we're going to talk about exponential derivatives. Friday, and the purpose of this, and then Friday we're going to review trig functions. Okay, so today, exponential derivatives. Friday, review trig functions. Monday, I'll give you your next take-home quiz, and you'll have a project check-in day for the drum roll project. Okay, so today we're going to discover formulas for the derivatives of exponential functions, and we're going to use them with some other derivative rules to solve optimization problems. Okay, so take a look at d dx of e to the x. If I want to find the derivative of that, can I apply the power rule? No, why not? Right, but why is it that and not x times e to the x minus 1? Yeah, so the power rule only applies when the x is the base and the exponent is a number, right? You can only apply the power rule when the x is the base, right? So we can't apply the power rule because the x is in the exponent now. Okay, so in the group activities of last class, you all conjectured a formula for the derivative of e to the x based on its graph. Okay, so if you were trying to sketch the derivative of e to the x, right, you could say, well, really far to the left, my tangent lines are all pretty flat, right? So when you go really far to the left, your derivative function is going to be near 0. And then at the point 0, 1, if you draw a tangent line, it looks like it has a slope of 1, right? So my derivatives, if I try to make a little chart like x, f prime of x, the x value and the slope of the tangent line, when we're pretty negative, like let's say like -3, -4, those seem like they're approximately 0, right? They're really close to 0, teeny bit positive. Okay. And then when x is 0, if you draw a tangent line, it looks like it's got a slope of 1. And then if I draw a tangent line at this special point, which is like 1, 2.7, the slope looks like it's close to 3, right? So 1, my slope is steeper, and it's like 3-ish. And then over here at 2, my slope's really steep, like maybe twice as steep as before, maybe 6 or 7. Right, so these are total estimates, but they give you an idea of the shape of the derivative function. So when I'm far to the left, I'm really close to 0, so I'm close to the x-axis. So these guys are like 0, 0, 0, pretty close to 0. And then at 1, my derivative is, at 0, my derivative is 1. And then at 1, my derivative is like 3-ish. At 2, my derivative is 6 or 7. And if I connect all these, it looks like I just recreated the same graph. All right, so we're going to look at a sort of a more sophisticated version of what I just drew using Geometry Sketchpad. So here's a graph of e to the x. Okay, and I'm going to drag that point A around, and over here on the left, y sub a, that's the slope of the tangent line at that point. So at 0, 1, the slope of the tangent line is 1. And then just going to drag this point around, and you can see the slope of the tangent line is approaching 0. So it's like super flat. In fact, it's registering as 0 once we go far enough. And then it's like just a little bit positive. It hits 1, and then it gets more and more and more steep. At an x value of 1, I can't get it to hit 1 exactly. Oh well. So it's my x value of 1, my slope is about 2.74, right? So you can see that the slope here and the y coordinate of point A are always the same, right? So my derivative function, it's got the same x and y values as the function itself. Slope of the tangent line, y coordinate of point A, same. Okay, so the book proves the fact that e to the x is its own derivative. I'm going to encourage you to read it, but I'm not going to go through the proof in class. So the derivative of e to the x is e to the x. Therefore, the derivative of e to some stuff will be e to the stuff times what? The derivative of the stuff. Just apply the chain rule if you're taking the derivative of e to some stuff. It's the easiest derivative rule ever, right? Taking the derivative of e to the x is e to the x. It's actually not hard to differentiate any exponential function, even if the base is not e. So the derivative of a to the x is a to the x times the ln of a. So the derivative of a to some stuff would be a to the stuff times the ln of a times the derivative of the stuff. So I'm taking the derivative of a to the x, right? A to some stuff. There's no product in there. So when I was taking the derivative, I ended up writing products, but the original function had no products. Depends on what the stuff is, yeah. Okay, so let's look at an example where we're going to use our new derivative rule. I want to take the derivative of 4x times e to the negative 2x. Actually, before we do that, what happens if I use this rule to take d dx of e to the x, right? According to this rule, my answer would be a to the x or e to the x times the ln of e, right? Which is 1, so that agrees with our original formula that it's just e to the x. So the e to the x rule is just a special case of the a to the x rule. Sure. Just keep getting e to the x, yeah. It's actually the first question in your group activities. I asked you to find the 100th derivative of e to the x. Good. Yeah, so it's e to the x. Yeah, yep. Okay, so now we're going to apply some derivative rules. I have several rules I'm going to have to apply here to find the derivative of 4x times e to the negative 2x. So I said the word times really accented because I'm going to have to use the product rule. That's 4x times e to the negative 2x. So think of this as your first and your second, or your f and your g, if that's how you like to think of it. Okay. So I'm going to have to use the product rule, and then I'm also going to have to use the chain rule within it. Yeah, when I'm working on taking the derivative of e to the negative 2x, I'll need the chain rule. All right, so the product rule says do the first, which is 4x, times the derivative of the second. And I'm actually just going to write down d dx of the second function. Just for one problem, I'm going to write everything out. You don't have to write everything out if you'd rather just jump right to writing the derivative. So this is 4x times the derivative of the second, which is e to the negative 2x. So first times the derivative of the second plus the second times the derivative of the first. So I have not actually done any of the derivatives within the product rule. I just wrote down the derivative of e to the negative 2x and the derivative of 4x. I still have to take those derivatives. Okay, so if I want to take the derivative of e to the negative 2x, that's e to some stuff So the derivative of e to the negative 2x should be e to the negative 2x times negative 2. Right, because my stuff is negative 2x, so the derivative of the stuff, negative 2. Plus e to the negative 2x times, what's the derivative of 4x? 4. There we go. I'm done. I could just circle it, but like I said, if you can do like 1 or 2 simplifications that make a big difference, go ahead and do them. I can see a really easy one to do here. I'm going to multiply the 4 and the negative 2, and that's it. So I have negative 8x e to the negative 2x plus 4 e to the negative 2x. All right, so I think that's it for the lecture portion of class. I'm going to have you work on some activities now.